and he's going to talk to us about adapting supervised machine learning approaches for hydrothermal resource assessments.
Thank you, Justin. Hi, I'm Stan Mordensky. So the USGS is gearing up for the next round of hydrothermal resource assessments. The USGS is mandated to produce these assessments on a periodic or semi-decadal basis. And for the better part of the last 3 years, I've been working with Eric Burns, Jake D'Angelo, John Lepore, and of course Pascal on finding ways to improve upon previous assessments. In 2008, the USGS released its most recent assessment. That assessment had some expert decisions in the workflow, and we view those expert decisions as potential opportunities where we can improve the workflow. Specifically, instead of relying as much on expert decisions, can we instead implement data-driven approaches or more data-driven approaches to minimize those expert decisions? So I'm going to be presenting a series of studies to you today, starting by asking, can machine learning predict hydrothermal resources as well as methods dependent upon expert decisions? And then move on to subsequent studies asking, how can we do even better? And I'll start with, yes, I hope to impart upon you that machine learning can do at least as well as, if not better than, the methods from 2008 that were dependent upon expert decisions. And in that process, I intend to demonstrate that simple but non-linear machine learning approaches are best, and we can demonstrate how valuable new data sets are. So the 2008 assessment predicted relative favorability for hydrothermal resources across the western United States. That is, this area is more favorable to hydrothermal systems than this area, red and blue respectively on these maps, which depict the predictions from the 2008 assessment for the two methods used, logistic regression and weights of evidence. This assessment was completed by gridding the western US into over 700,000 2K cells, in which we had 278 known hydrothermal systems, or 278 cells that were known positives. But, like Pascal said, the remaining cells were unlabeled. Now, these known positives were correlated with 5 input feature sets: heat flow, distance to nearest fault, distance to nearest magmatic activity, seismicity, and stress. And although these data sets are continuous in nature, due to the tools available at the time of the 2008 assessment, these data sets had to be binned. And this is where expert decisions enter the workflow. How many bins do we use? How many bin boundaries, or which values for bin boundaries do we use? These were decisions completed by Williams and D'Angelo. But this begs the question, how did these expert decisions influence the model? Was bias imparted? Well, if we use the exact same data with data-driven machine learning approaches, we can come to an answer. Now, there are some challenges in applying these data to supervised machine learning. Like you heard me allude to, we didn't have no negatives. Additionally, we had extreme class imbalance, or the sparsity of hydrothermal systems was in play. And to address these two challenges, we used a custom train test split that randomly selected negatives from the unlabeled points in a ratio that roughly matched the occurrence of hydrothermal systems that we roughly anticipated to see in the western United States. We applied this train test split, this custom training strategy, to 7 different machine learning approaches of increasing complexity. And then we compared those predictions to the predictions from 2008. So with those being the 2 prediction maps from the 2008 methods, here are the 7 other maps from the machine learning approaches. And in general, highs are high and lows are low consistently with respect to regions. And this is assuring, but the question then becomes, which of these did best? And this is difficult to answer from the perspective of the 2008 assessment predicted relative favorability. One area is more favorable to a system than another, whereas the machine learning methods do that as well as predict known positives and negatives, or predict positives and negatives. So they can use performance metrics like accuracy, precision, and recall, whereas the methods from 2008 cannot. So we had to get creative. And we turned to these cumulative distribution functions that Pascal shared a moment ago. I'll save you the math and simply say the lines on this plot represent the predictions for known positives from each different approach. The further to the right the line, the more confident that approach is in predicting those positives as being positives, the known positives as being positive. A perfect model in this case would have those lines just about vertically all the way to the right. So in general, we see the methods from 2008 and most of the machine learning methods having substantial overlap. And that's a way to say that they didn't really do that much better than one another, with one exception. And that's that solid blue line further to the right than the others. And that is a method that used an algorithm called XGBoost, which is decision tree dependent. And the thing about XGBoost in this case is that it was the simplest nonlinear approach that we investigated. And this made some sense from the perspective of what we were trying to do. The simplicity matters in that in machine learning, the more complex the approach, the more data you really need to train a good model. We only have 278 known positives. That's not a lot in machine learning. So the idea that the simplest of something did the best makes sense. The nonlinearity makes sense. The decision tree component makes sense from what we were trying to model physically. Hydrothermal systems operate in Goldilocks zones in terms of geological conditions. If you have too much of something, say stress, not enough of something, heat flow, or vice versa even, the hydrothermal system may not exist. The decision tree nature of XGBoost, its nonlinearity, allows us to target these specific values that are of consequence to hydrothermal systems. We also have different ways of measuring which of the different input features are the most important. And we have several ways, in fact. And we used a lot of them, given the different approaches as depicted on the left y-axis, per different features on the right y-axis. And this is a spaghetti plot. It's messy, I know. Focus on the overall shape, with the idea that further to the right means more important and further to the left means less important. And what that means is that heat flow and distance defaults were the two most important features across the different approaches, whereas the least important features were seismicity and stress. So from this, we have strong reason to suggest that machine learning methods can do at least as well as, if not better than, the methods from 2008. And that XGBoost, or simple nonlinear approaches, are optimal with geothermal data. And we can demonstrate how valuable the different data are. But this creates a series of hypotheses about how we can do better. One such is that the value of new data should be examined. That is, can we add new data sets and make a better model? And we did exactly that. We added two new feature layers, dilation strain rate and shear strain rate from Zen 2022. And we added these to the original 5 features from the 2008 assessment using the XGBoost approach. And then we created a third model that removed the 2 least important features from the 2008 assessment, so seismicity and stress. If we return back to the CDFs, I'll try to use the laser pointer, but I'm not sure that's not going to work. Okay. So the solid line represents our certainty or our probability of predictions for the known positives using the original XGBoost model, the original 5. When we add the shear strain rates to create a 7-feature model, the dashed line, we move a little bit to the right. We're a little bit better at predicting our known positives. When we remove stress and seismic event density, that line, the dotted line now, moves a little bit further to the right. We increase our ability to predict known positives by removing some of the data. And this is a little bit counterintuitive. It's not that these data are incorrect or wrong. It's the idea that in machine learning, when you add new data sets, you're increasing the complexity or the dimensionality of the space, the volume. That's not the right word to use. Volume's a 3-dimensional something. You're increasing the space in which you're trying to draw a decision boundary. If you're increasing the complexity of that decision boundary, but you're not adding more information, in this case, the idea of more hydrothermal systems to populate that space, drawing that decision boundary is increasingly difficult. So by removing these 2 features, we simplified the decision space, and they weren't terribly informative. This lends to the idea that we can add new features, but the new features need to be at least as valuable to offset the cost of adding those new features. And with that in mind, we need strategies to identify which layers, which features are best, and use the fewest possible. The next question we had, which is Pascal's presentation in repeat, is how the selection of negatives may impart bias. And if you missed Pascal's talk, he took the data from the Nevada Machine Learning Project, and he applied XGBoost and logistic regression using their training strategy of their known positives and their expert selected negatives. Then he tried our training strategy for the random selection of negatives. And what he demonstrated was that the predictions when using our custom train test split, our training strategy improves the model predictions. But one of the takeaways that he had is that these trended features, they still impart some kind of signal into the predictions. And the question then becomes, well, what can we do about that? The answer is to engineer better features. And that's what we're working on next. Jake D'Angelo, a member of our team, recently released, I believe 2 weeks ago, a detrended elevation map for the Great Basin, with the idea that elevation is lower toward the western part of the Great Basin and higher toward the east. Now, that might not necessarily matter as much from the perspective of predicting hydrothermal systems, in that in the Great Basin, one would expect hydrothermal systems to have some kind of relationship to the interface of the basins and the ranges. Whereas if we just use raw elevation, we're using raw elevation as the signal. But by detrending the elevational trend from the original elevation map, we can create a detrended elevation map that creates a clearer signal for the presence or absence of hydrothermal systems. So in conclusion, machine learning can do just as well as, if not better than, the methods from 2008. And we have evidence to suggest that we want to select the best, fewest data layers possible. And like Pascal demonstrated, we need to use a training strategy that selects all the different types of negatives. But the real battle ahead of us is engineering the most informative features possible. Because we have so few training data to go off of, we're susceptible to the effect of increasing the complexity of the dimensional space that we're trying to draw that decision boundary in much earlier than other forms of machine learning. Typically, that becomes a problem at hundreds or thousands of features. We're seeing that at 5 to 7. And there are two ways to really fight this. Have more labeled points or targets that we're trying to hit, more hydrothermal systems. That's not really an option. Otherwise, we have to engineer better features. Acknowledgements and references. And I hope you have questions, but I don't believe there's time, so shoot me an email or hit me up later today. Thank you.